Welcome to this complete guide on acids, bases, and salts. We'll explore topics from the pH scale to neutralization reactions and making salts. In this video, we will cover acids and alkalis, the pH scale, indicators, neutralization and salts, strong versus weak acids, and everyday uses. We begin with Chapter 1, Acids and Alkalis. These chemical opposites are found everywhere, from lemons in your kitchen to bleach in your bathroom. An acid is a substance that produces hydrogen ions when dissolved in water and has a pH below 7. Key properties include a sour taste and reactivity with metals, bases, and carbonates. A base or alkali is a substance that neutralizes acids. Alkalis dissolve in water, producing hydroxide ions, and have a pH above 7. They often feel soapy to the touch. Here's a quick look at the differences between acids and alkalis. Acids have a pH below 7, produce H+ ions, taste sour, feel corrosive, turn litmus red, and examples include HCl and hydrogen sulfate. Chapter 2 is about the pH scale, a simple 0 to 14 scale that tells us exactly how acidic or alkaline a solution is. The pH scale ranges from 0 to 14. Acidic solutions are 0 to 6, neutral is 7, and alkaline solutions are 8 to 14. Stronger acids are lower numbers, and stronger alkalis are higher numbers. Everyday substances range across the pH scale. Battery acid is highly acidic at pH 1. Cola is mildly acidic at pH 3 to 4. Pure water is neutral at pH 7, and bleach is strongly alkaline at pH 13. pH matters worldwide, impacting biological systems, agriculture, and industry. Remember, the pH scale is logarithmic, meaning each step is a 10x change in H+ concentration. In Chapter 3, we look at indicators. These substances change color to reveal whether a solution is acidic, neutral, or alkaline, making the invisible visible. Litmus is a classic natural dye indicator. It turns red in acidic solutions and blue in alkaline solutions. Its limitation is that it only shows if a substance is acid or alkali, not the precise pH value. Universal indicator is a mixture of dyes that gives a full range of colors corresponding to specific pH values. It ranges from deep red for strong acid to violet for strong alkali, providing more information than litmus. Other common indicators include phenolphthalein, which is colorless in acids and pink in alkalis, and methyl orange, which is red in acids and yellow/orange in alkalis. Red cabbage is also a natural indicator. Choosing the right indicator depends on whether you need a quick acid/alkali check or an exact pH value. For accuracy, a pH meter is the most reliable method, as indicators only give approximate values. Chapter 4 covers neutralization reactions. This is the process where an acid and an alkali react to cancel each other out, resulting in a salt and water. The general word equation for neutralization is acid plus base yields salt plus water. In the ionic equation, H+ ions from the acid react with OH- ions from the alkali to form water. The remaining ions form the salt. Neutralization often involves titration. Acid is added to a flask with an indicator, then alkali is added drop by drop. The indicator changes color at the endpoint, showing salt and water have formed. There are three main types of neutralization: acid plus metal hydroxide, acid plus metal oxide, and acid plus metal carbonate. The latter also produces carbon dioxide gas, which can be seen as bubbles. Neutralization is an exothermic reaction, meaning heat is released when the H+ and OH- ions bond to form water. This causes the solution's temperature to rise, which can be measured with calorimetry. Chapter 5 focuses on making salts. Salts are ionic compounds made from the reaction between an acid and a base. The method used depends on the required salts. The name of a salt is derived from the acid and base used. Hydrochloric acid makes chloride salts, sulfuric acid makes sulfate salts, and nitric acid makes nitrate salts. The metal comes from the base, and the negative ion from the acid. Method 1. Titration is used when both the acid and alkali are soluble, like making salts from soluble bases. You use an indicator to find the endpoint, then repeat without the indicator to get a pure salt solution, which is then evaporated to crystallize the salt. Method 2 involves adding excess insoluble base to the acid, warming it, filtering off the excess solid, and then evaporating the filtrate to crystallize the salt. Using excess solid ensures all the acid is neutralized. Method 3 is precipitation, used for making insoluble salts. Mix two soluble solutions. The precipitate forms immediately, Then filter, wash, and dry the solid. Lead iodide, a striking yellow precipitate, is an example. To compare the methods, titration is for two soluble reactants and uses an indicator. Excess solid is for an insoluble base, filtering the solid. Precipitation is for insoluble salts, where you filter the precipitate. Chapter 6 explores strong versus weak acids. The difference in acid strength is not about concentration, but about how much the acid ionizes in water. Strength is defined by ionization. Strong acids fully dissociate in water, releasing all their H+ ions. Weak acids only partially dissociate, establishing an equilibrium. Examples of strong acids include hydrochloric acid, sulfuric acid, and nitric acid. They fully ionize in water, making them highly corrosive and useful in industry. Weak acids, such as ethanoic, carbonic, and citric acid, only partially ionize. This means only a small fraction of the molecules exist as ions at any time, indicated by their reversible equilibrium symbol. The chart shows that even at the same concentration, strong acids have a much lower pH than weak acids because they release far more hydrogen ions. A lower pH means a higher H+ concentration and a faster reaction rate. It's important not to confuse concentration and strength. Concentration is the moles of acid per liter of solution. Strength is how completely the acid ionizes in water, a fixed property. In Chapter 7, we explore the everyday uses of acids and alkalis. These substances are essential in various aspects of our lives, not just in the laboratory. Acids are vital in daily life, such as the hydrochloric acid in your stomach for digestion. Fizzy drinks use carbonic and phosphoric acids for flavor, and vinegar is ethanoic acid used in food preservation. Alkalis are equally important. They are used in soaps and cleaners to lift grease, as well as in agriculture to neutralize acidic soil, and in toothpaste to neutralize mouth acids. Industrially, sulfuric acid is crucial for fertilizers and batteries. Ammonia, a weak alkali, is key for nitrogen fertilizers. Sodium hydroxide is used in paper, soap, and wastewater treatment. Neutralisation chemistry is crucial for treating acid rain, which is formed from sulfur dioxide and nitrogen oxides. Solutions include adding lime to lakes and using catalytic converters. Here are key equations to remember. Reactions between acid and metal hydroxide, metal oxide, and metal carbonate all produce a salt. The ionic equation H++OH- yields H2O is common to all neutralizations. For exams, always include state symbols in equations. Remember the difference between strength and concentration. Know your indicators and the rules for naming salts. You've reviewed the essential topics: acids and alkalis, indicators, neutralization and salts, strong versus weak acids, and everyday uses. Keep practicing, and you'll master this subject.